Center and here in our home state, Illinois, and earned her bachelor's and master's degrees, both in civil engineering and environmental science from the University of Michigan. She also has earned her honorary doctoral degree in environmental science from Lewis University. She has an extensive experience, not only in private industry and academic research, along with her really nice portfolio ranging from vehicle components to transportation as a holistic system. And I hope that you share the same sentiment that I have in looking forward to really hearing her perspective about how innovations are really reshaping our mobility. But before we proceed, I'd like to invite Professor Al-Kadi to share a few words.
Yeah, thanks, Anjali. And we are very, very pleased to have you with us. I think Anjali, she has a very good introduction of our speaker today, but no doubt she is a very well-rounded speaker when it comes to the transportation. She has an amazing experience that I'm sure you're going to agree after you hear what she has to say today. And we're looking forward to our collaboration. We start talking about it, and we're very, very pleased that you could join us today.
Well, thank you so much. I appreciate the opportunity all. And sorry for some technical glitches that we're having here, but hopefully we'll be able to power through it all. And this is one of those perseverance moments, and we all make the best of it, right, as engineers. So thanks for carving out some time today to spend with me. And these opportunities always give me the chance to reflect back and to think about career, particularly as you talk to students, grads, undergrad, faculty, and what rewards you've really had within your career and what sparked the juices. From the introductory that was so kind, you learned that you essentially got 40 plus years in this field of transportation. And went into transportation really from school. These were back in the days where the Clean Air Act was just enacted, and we had some real serious challenges with brown cloud and ozone and terrible air quality in various regions of the country. And our fuel economy and energy resources were being challenged, obviously, with oil imports and other things. So a lot of great work early on that I did in vehicle space for emissions and evaporative control and calibration work on cars, and really trying to not only improve the vehicle, but improve fuel. And so I ran some chemistry labs during part of this time too, to understand how to come up with better recipes, if you will, for cleaner burning gasoline. So great opportunities that I had early on in my career, making a difference, in my opinion, for societal goals, and at the same time working for a company and meeting their needs. After that stint for really 20 years in the research world, I went on to frontline product development, and I was afforded many opportunities, and it was wonderful because everything from at the time we had directors over a particular discipline within an automobile. So things like, body, chassis, interior, electrical, powertrain. And I served as an interior powertrain director and also as an advanced vehicle engineering director. So I had the chance to see everything up front in the vehicle, all the way to the manufacturing of the product in, 6 months or a year after that, even in the manufacturing plants. So good window into the product development process. And I also spent 6 or 7 years in regulatory development. So on fuel economy and emissions and safety regulations and where we needed to go. And some of my proudest moments really are from the technical contributions that I could bring to propose legislation or rulemaking, and justification for those sound approaches that I was in advancing. So I really loved that period of my career, and then transitioned after some self-reflection over, what's next, and went closer back to those roots that I had in the research field. And so I joined Argonne, and I've been here for about 12 years now. Lead a team of about 100 engineers and scientists in the Center for Transportation Research. And we're really championing, how to improve emissions and air quality and fuel economy, all leading to decarbonization of the transportation sector. And of course, electrification has a big part of that. So it was a natural segue career-wise. And again, it was a reflection internally done over, what juiced me, what kept me still getting up each morning and just loving mobility and transportation. And so this took me back to smaller teams than what I had within industry, but still, very rewarding work. So I just wanted to give you a little bit of that background, a little long-winded, sorry for it, but just as you're thinking through your career choices too, I just encourage you to always reflect on what's important to you, how you want to make your contributions, and assure that you're aligned in your career choices that you make. The next slide then really puts it into context over the Department of Energy National Labs. Angela, if you'll advance the slide. And it really is the Department of Energy having 17 national labs across the country. And we all have separate focus areas, I would suggest. In transportation, you're probably familiar, of course, with Argonne, your neighbor in the state. But beyond that, NREL out in Colorado, the National Renewable Energy Lab, they do a lot of wind, solar, renewable energy, biofuels, and some of that for transportation beyond the grid. Oak Ridge National Lab down in Tennessee is another transportation lab, and they do an awful lot of materials development and after treatment work on engine combustion devices, let's call them. Out at Lawrence Berkeley National Lab, they're another big lab in transportation, and they do quite a bit of modeling work as well for the Department of Energy and Transportation. So the next slide, it really shows the breadth of what Argonne does, because it represents a multidisciplinary expertise about science and technology. A few years ago, the Department of Energy was Vehicle Technologies Office was very focused on individual components, batteries, engines, electric machines, how you make all of those pieces and parts better performance, lower cost, easier integration. It was really component focused. We still play heavily in that area, and it is a part of the DOE portfolio. They, of course, grew into vehicles. Those parts and are all wonderful, but they have to be integrated into a vehicle and ultimately sold. And so we do significant vehicle modeling to forecast fuel economy or to help down-select powertrain architectures with autonomy as one of the tools. And we also do component sizing within some of those tools as well. Of course, as I talk about vehicles, it segues immediately over electrification and grid and interoperability. And interoperability really means more than just, will the electric vehicle supply equipment, the EVSE charger, fit into the coupling, the hole within the vehicle to be able to charge, but it's all about the communication layers, the transactions, the security, the rate of charge, the time of charge, how you help enable stability within the grid, and how you put renewables back into the grid beyond the base load. So quite a bit of work at Argonne with the grid and interoperability. And then relatively new in the past 4 to 5 years is an expansion of the DOE VTO portfolio into transportation systems. We've been doing this work for years for the Department of Transportation or FEMA, but start to think about the entire landscape of transportation, the roads, the vehicles, the buildings, the traffic signals for infrastructure, all of it as a system. And of course, it was changing with all sorts of new modes of transportation and human decisions that are being made and real-time information and new technologies. So that it was a relatively new field of science, for VTO that we brought forward, and we're very fortunate that we had tools already prepared to be able to bring to this science discipline. And I'll just encourage you to think of that ending point that I just said, transportation systems. So start at components, go to vehicle, go to multi-vehicles, go up to transportation system. Because at the end of the talk, I'll come back to you and tell you that that's really not the end, and there's more to do. This next slide that says Argon Solutions for Decarbonization, not intended to read, but it's really the way I bring a mindset to the research. And I think it ultimately has influenced my team. You know, early on, I would say with some resistance because research versus an industry focus in different timelines kind of can present some tension. But my way of thinking is always about strong capabilities in science and technology. And then it really has to have an application in the end user. And the end user helps define what those research capabilities must be, the vehicle or the component performance requirements. And that has to be a very iterative process all the way through so that the research has a landing place and a real application that's been identified. So I really just want you to pay attention to the rows going across that say science and technology and application of that science, and then where do I deploy it? And if I just pick on advanced combustion as one example, we do significant computational fluid dynamics in this space, fundamental knowledge about combustion, and that leads to computational codes that we do on our own machines with HPC and AIML. But then we translate that code into things that are a little simpler, such that industry can readily adapt to it and use it on their desktops that are advanced. And that leads to improved design and development of engines or components. And then in the very bottom left box, then I just speak to some of those industrial customers that we have in this space. And of course, it grows all the time. The next slide then really it talks to a different piece of our portfolio that I have within the Center for Transportation Research. And it's one of those heartfelt things for me where I and the team give back to the professional societies. And this is about 35 years of the advanced vehicle technology competitions that developed the next generation of automotive professionals. And it's a 4-year program that emulates the product development cycle within the auto industry, such that year 1, you're doing modeling, you're identifying customers, you're down selecting architectures, you're starting to think about what components you might need. Year 2 is components and integration. Year 3 is unique selling propositions, the innovation piece of it. And year 4 is integration and refinement. So it's a long program, up to 16 North American universities in a very competitive process to get into this competition with headline sponsors. And currently it's the EcoCar Mobility Challenge. We've got another year through 2022, May of 2022, before this series ends, but we'll be kicking off another series probably later this fall sometime, just to get the enrollment process moving forward. And this program morphs that it started with advanced powertrains, so think of hybrids and fuel cells, electric vehicles. And a couple of years ago, we curtailed a little bit of that development activity and said we really needed to include the connected and automated vehicle research space to help train and develop engineers and scientists in that space as well. So about 40% of the program now is on connected and automated vehicles, or CAVs as we call it. So I'm going to take a few slides here next and talk about transportation. And of course, you're interested in the field by your attendance today. But transportation, we're always so fortunate because it's relatable science field to everybody. you know, whether it be your neighbor, your mom and dad, you know, your kids, everybody understands transportation and mobility. And there's challenges associated with transportation. That we've got population density that's increasing in certain regions. We've got an aging population as well. This can lead to congestion and also greenhouse gas and air quality concerns that we have. And overall, transportation costs are the second highest expense that a household would have beyond housing into the family budget. These are just a few examples of transportation issues that are external driving into the scientific field and things that we need to address. And of course, congestion, as I talked about some of these factors, you know, it's not just congestion and inconvenience. It's really more than 40 hours of your life a year on average that you are sitting in traffic incremental to what your normal commute pattern would be, or about $1,300 a year that you forego, you know, just in congestion rather than productive work. So there's an impact on the GDP as well. The next slide really speaks to mobility. You know, transportation, mobility. What is mobility really about? And my premise is that mobility is the quality of a network or a system to connect people together. It's all about this connecting people to opportunities, right? And it needs to be efficient, affordable, and it needs to be equitable. And then we have to have measures to assess whether the policy, the new technologies, the choices that you and I are making, are they better to the system overall, or are they not? So here we are, mobility, the quality of a system to connect people to goods, services, and employment, to define a good quality of life. And what do we want to connect to? Obviously, education, good employment, good healthcare, good food, and of course, green space and leisure as well. So it's more than just the quality of the roads and bridges. It's really about the opportunities instead that we're giving to everyone for better access. The next slide then shows that it's complex when I talk about transportation and mobility. When I look at transportation systems and just start to pull things out of your mental mind space, you think, well, okay, it's vehicle technologies, absolutely. You know, hybrids and electric and fuel cells and diesel and alt fuels. It's vehicle technologies, and it's goods movement. You know, we all order things and we want, you know, the beer delivery truck to come to the bar, and we need it at the grocery store. So it's people and goods movement, but it's even more than that, right? It's the choices that I make and the time that I want to travel and what modes I might consider. So that's traveler behavior that's into it. It's about transit and e-commerce, you know, where I substitute some of my travel with e-commerce choices instead. Connected vehicles, meaning the communication between vehicles and between the infrastructure, the built environment, traffic lights, traffic signals, curb management, just as an example, EVSE charging locations, automated vehicles on our path to automation, SAE levels, you know, 1 to 5, when are we going to get there? What are the benefits and what are the risks of some of that technology? But each one of those is not a lone actor, right? They all impact each other in a system. So you can't just look at personal vehicle travel, shared vehicle travel with name Uber and Lyft, because that has to interact with the Amazon delivery truck or the United States Post Office truck or FedEx trucks. So it's a very complex system overall. And that's really some of the tools that the DOE complex, VTO, Vehicle Technologies Office, brings to this space. So the next slide talks to a modeling workflow. About 4 years ago, the Department of Energy kicked off a smart mobility project, really to look at modeling this big transportation system and new modes coming up. So where did we start? We started in the heart of agent-based transportation modeling, ABM modeling for mesoscopic simulations. For Argon, Polaris is the tool we use. Lawrence Berkeley has a tool called Beam. But then, of course, we have to feed into that. And our goal is to have these large ABMs for urban regions. For example, we have Chicago, but it's 80 square miles. It's, all the way to Wisconsin and to Indiana, essentially, right? And downstate in Illinois. So it's big regional modeling, but I need other inputs into it. So microscopic traffic flow, multi-vehicle control, the trip profiles. I spoke to traveler behavior, goods movement, system control, all of that being in the center, the heart of it. But even more, I need to know what market adoption rates are going to be for various technologies, what the land use is going to be, and not just today, but taking a look at population trends and employment trends, EV charging as well on the left-hand side. And then some of the outputs and measures and metrics are too numerous to mention, but everything from greenhouse gas and CO2 and miles per hour, is certain congestion metrics for speed, and more, right? Personal hours traveled, or maybe it's DMT. So we have a slew of measures and metrics that come out of this workflow. We instituted this workflow across the DOE transportation labs. There were 5 labs in particular that were engaged in this for 3 to 4 years, and we just launched in this past year now another 3-year project. I can't remember exactly how many projects, but certainly more than a dozen, to advance the understanding and the knowledge and get closer to the stakeholders and deliver tools and models over to them to be able to do scenario planning themselves. So some of the results then from the smart mobility workflow is really what I want to show you in the next few slides. And so we'll go by pretty quickly because they're really result slides more so than the details of exactly how we did it. We did publish Capstone Reports a year ago now. I can provide that at the back end of this talk because there's 5 Capstone Reports and each of them are 100 to 200 pages. And there's even PowerPoints on each of Capstone Reports as well to guide those that are interested in the space. So the next slide is just an example of connected and automated vehicle research that was done under the smart mobility umbrella. And the first slide that reads vehicle and powertrain control offers sizable benefits. What we used was our Roadrunner and our Polaris tools for vehicle-to-vehicle communication, and took a look at a conventional vehicle, meaning internal combustion engine, as compared to an electrified vehicle, and then tried to understand that with situational awareness and communication to traffic lights as an example to the infrastructure, so that vehicle-to-vehicle and vehicle-to-infrastructure communication, what was the potential energy savings that I could find? And it was up to 20% or 21.8% in an urban area as an example for that conventional vehicle. So again, trying to help DOE and others, areas to hunt, what's important for some that are either in the vehicle development space, some that are in the municipalities that are wondering where to put their money for investment that's very limited. And of course, this is showing that intelligent traffic signals and vehicle-to-vehicle communication, or V2X, V2I, are very important for energy savings. The next slide that reads individual ACC and it's a walk of 3 slides. And I will say that these findings can be a little bit controversial. This was a study of Volvo vehicles, actually field vehicles, in I think 1,800 trips, 18,000 trips that were taken. And so we looked at the benefits, the individual benefits of the car that I own on the road. So if I'm self-centered and I'm thinking about my benefit of my vehicle that I just purchased that has ACC as one of the optional technology packages, what we found was a 5 to 7% decrease in energy for my car because of that ACC function when it was employed. So good news, right, for me as the owner of the car and for my wallet. However, again, remember I want to look at a systems lens instead. And so the next slide that says high ACC penetration may actually negatively impact traffic flow. And this was a look at, a corner case, the extreme of 100% ACC. And we found fuel consumption could, remember before I had a decrease, an individual vehicle decrease, this is a fuel consumption could increase on the system by up to as much as 60%. And you're like, oh my gosh, this is supposed to be good technology. It's supposed to be helping energy savings. What went wrong, right? Well, the issue is that you've heard of string stability. You've heard of the lack of vehicle-to-vehicle communication causing phantom traffic jams and amplification of speed changes that happen within this string. And so, this is a future that few of us really want to see. So the next slide then overlays cooperative active cruise control, where now I've got vehicle-to-vehicles talking to each other, seeing ahead electronically, if you will, where you and I as physical drivers don't have that opportunity. And so all of a sudden on a total system look for the vehicles that have this feature as well as those that don't, with this communication and automation, I can have a fuel savings back up to 20%. So this was, great news, and it was just at a 60% implementation rate of CACC on stretches of highway. So exciting, it's a path to get to CACC, ACC is the starting point, but obviously a path that we should continue on to try and net these type of savings. The next slide really speaks to shared mobility, and I'm just going to talk about, one slide of research within a few of these next domains. And so as you think of shared mobility, in COVID times, less so, but before, many of us probably, have the Uber and the Lyft app or other Via apps on our phone to dial up a ride, right, and get from point A to point B as a low-cost fee per mile charged. So shared mobility, next slide, please, really can have contradictory impacts as well. When I talked about the workflow, we used scenario-based framework. And so we looked at low sharing on the right-hand side and high automation. So this is, let's say, a level 4, level 5 autonomous car, but it's in my own garage and it's optimized just for my household use. Conversely, the picture over on the left-hand side of your slide is high sharing and high automation. So it's level 4 and level 5 automated vehicles, but they're in a shared fleet operational business mode. And you see vastly differences, right? The high sharing, high automation on the left says I can save energy by 23%, vehicle miles traveled can go down 18%, passenger mile travel stays neutral, and speed within the network can increase 17%. Conversely, see a lot of red over on the right-hand side, low sharing, high automation, because now I have deadhead trips, because I'm not optimizing a fleet, I'm only optimizing for my household travel. Energy increased 22%, vehicle miles traveled 25 up, 7% on passenger mile travel, and 18% reduction in the network speed for significant congestion. So, you know, these are the type of findings that can help inform which direction we want to encourage. And then, of course, DOE doesn't directly get involved in policy, but this kind of knowledge can then inform those that are in that position to enact and create policy. A slide on the built environment is next, and I segue immediately to the optimizing signal controls. I want you to think about vehicles that now are talking, and I use this literally, right? Talking to the infrastructure, to the traffic signals. And this was a section in Washington that we looked at for 35 intersection controls with smart traffic signals and SPAT. And then the vehicles controlling the traffic signals based on cues at different intersection points and what the traffic was. And we found that with 40% cab penetration, we could actually have an 8% reduction in delay. In other words, how often you had to stop, and an 8% reduction in energy. And of course, you know, another thing that's really intuitive to everyone is when you pull up to that traffic light and you're stopped, and yet there's no cross traffic coming at all towards you. And so there you are for, you know, your 45 seconds or a minute, depending on the control signals, right, awaiting your green light. So here's a real opportunity to try and improve with system controls and situational awareness, the energy consumption that we have. Next, I'll talk very briefly on goods delivery, and just an example that's a little further from what you might think of for goods delivery today, and it's about drones. So we did field testing of drones and for package delivery at different elevations to understand what the energy consumption was for various package size and weight, and how that compared over to, let's just pick a light duty electric vehicle as an example. And so this really was measurement of energy consumption, and you can see 15-pound package as compared to a light duty EV with 30-mile-an-hour steady state, not equivalent energy consumption, but interesting nonetheless. And of course, the EV could carry more than a 15-pound package and all, but it was really just trying to bookend where they are as you compare different options. We also wanted to make sure that we were covering transit, and I'm going to come back to this in more detail under a COVID scenario toward the back end of my talk. But know that transit is just critical to mobility for movement of passengers in an efficient manner. And so we were asked to take a look at just a hypothetical: if you remove transit completely from the Chicago region, what would happen? Of course, people still at this time wanted to move. And so it required personal vehicles or TNC and others services. And so we took a look, again, radical, what if, and energy and DMT, VHT, and network speeds. And again, it wasn't just the central business district, it was the region. You see overall the speed reduction as well. We studied e-commerce. I'm watching the time, so I'm going to continue on here. E-commerce, and wondered about an extra package delivery to my house as compared to me running to the local mall, brick and mortar store instead. Typically, a delivery route has, let's say, 120, 140 stops a day for a particular truck. And so if I just add one more stop on, about, a little less than a half a mile extra travel that would be incurred by that, as compared to if I actually went to the brick and mortar and came back again, it'd be 7 to 8 miles one way. So clearly an efficient extra delivery is a far better choice than what a single personal trip that's incremental to other businesses being conducted. So that this is the cute place to say, put it in your cart and not in your trunk. So we can't forget traveler behavior, and that is the next couple of slides that I'll address. And in particular, we all ascribe a certain value, a monetary value, even if you don't know it, to your travel choices, and maybe your frustration with your travel, the time you travel, and all of that influences the way you interact with the travel system. And finding has shown that transit users will pay $7.60 an hour to reduce travel by 1 hour, and drivers will pay even more. This is a really ripe area of study. It's very impactful. As one of the strong levers in any transportation system analysis is the value of travel time that is assigned to various communities, and getting that right is key. So that's a continuing area of needed research, I would say. And then as we talked about traveler behavior and decisions that we make, we ascribe that automated vehicles are going to have a major effect on travel behavior on this next slide. Right now, there's a cognitive burden of driving. You're sitting behind the wheel, you're paying attention. At times you're feeling stressed out because of all of the intake that you're managing to be able to operate that vehicle. However, if you had an automated vehicle, level 4, level 5, and even at times that level 2+, where you've got highway speed features for you to be able to unburden your driving experience, the finding is really that your circle of reach will expand, your activities will expand, that you'll consider that restaurant that's farther away in the gym or other leisure activities, such that your personal mile travel will likely increase as we have higher levels of automation and VMT as well. The next slide talks to freight, and just a couple to say why are trucks important. And the bar and pie chart that follows is freight movement is going to be increasingly important because the light duty segment continues to improve, as does the medium duty and heavy duty for energy efficiency. We're about 33% of energy consumption today in the medium duty, heavy duty sector. But the next slide really says that in the not too distant future here, we're going to be 50% of the fuel consumed is going to come from medium duty, heavy duty. So we know that advanced technologies, telematics, the ITS back in, the connectivity, and other features, electrification, and are going to be ever more important into this heavy duty sector as well. Platooning, the close coupling of cars or trucks is one of the things that we think we'll probably see in the very near future coming up as business models are developed to encourage this as well, with a 7 to 13% reduction. And I just want to segue now to COVID, because things have changed, and the impacts could be short-term or long-term. And this is really just hypothesis for many people at this point, right? Is telework, for those that are able, is that going to continue where my location, where I buy a house or where I reside, is no longer tied to my employment? That will have significant changes, right? If I am reluctant to have shared use rides, what's that going to look like? Is that going to increase personal car ownership, or is this short term only? What about transit and recovery of transit as an example? Is that around the corner, or is it not? So all these COVID impacts and on transportation are really still an unknown for us. You know, the e-commerce surge that continues and was already well underway before COVID, but now every day is like, you know, a Black Friday or the Commerce Day right before the holiday season in December. So I would just pause and say there's disruption, there's radical change that happened during COVID, and the sustainability is not well known at this point in time. The next slide, it talks about a COVID study that Argonne did under the federal government CARES Act funding, working with the Chicago Transit Authority, CDOT, and others, really to understand with transit ridership so depressed with COVID and capacity limits, you know, what was the forecast or what were some of the scenarios and the outcomes that we could envision. So this was a very close collaboration. And of course, ridership was way down on buses and on trains, rail, and personal car initially was down with the stay-at-home orders and then rebounded, as well as the system overall. So a lot of rebounds in the car and truck lanes. However, on the rail in particular remains depressed, and in the bus that a lot of essential workers really rely on, still low as well when we cut the data here, I think by the end of January in this study. So what do we want to look at? A couple of big factors were telecommuting and how many workers would continue to telecommute if given that option. And then risk perception from riders on transit, right? How they perceived risk of transmissibility of COVID for their willingness to get into a shared mode as compared to avoidance of such. On the right-hand side, you see different scenarios we ran for telecommuting with a baseline of about 4% of the people that commuted, telecommuted as a routine, even advanced of COVID. And then we looked at different, 15, 11, 8% doing daily telework and some hybrid models in there as well. Also looked at this transit risk perception model, and that was developed by UIC and ultimately with Arizona State as well. But we were fortunate to have that information for Chicago, looking at the risk perception, medium and high levels, and how that influenced traveler behavior and choices. The next slide really just sets up some of the scenarios that we did, and I'm just going to have one slide of results after this that talks about bus and subway boardings that were reduced because of capacity. And then we wanted to look at congestion effects on the economy and the user experience from transit. So we evaluated service cuts at 20% and 55%. We evaluated telecommuting at medium and high and low levels, risk perception at medium and high, and then load limits, the capacity that I spoke of. So multifactorial analysis that was done with scenarios through the Polaris tool, and a lot of HPC and AI ML applied to it. This slide really is a summary of some of that results. You see on the left is a Polaris model that is a visual representation of the study. In the walking chart in the middle shows service cuts plus medium telecommuting plus risk perception, and what is due to energy, greenhouse gas, or discretionary trips as an example. The green bar being a 20% cut in service, all hypothetical, and a 55% cut in service. And what do you see on energy and greenhouse gas with the numerical values there? This analysis also lets you look at equity, because as you cut bus for routes or for frequency of service, a lot of reliance on bus for essential workers. And so, there's a disparate impact along certain routes and zip codes in South Chicago or West Chicago as an example that needs to be considered for an equity lens as well. And then CTA in particular brought in expertise to say, okay, a reduction in discretionary trips, a reduction in workers in the central business district, for example, that's up to a $7.2 billion economic loss overall. The next slide I'm going to skip, which was just the key findings of it. The next moves to decarbonization of transportation and acting with urgency. And I just have 2 more slides here. And I take you back to the beginning where I said, remember, we're at transportation system, but this should not be the end point. And so it's not my next end point, I'm just moving the goalpost a little further to say I really need to look at systems of systems beyond the transportation system. I should be considering the buildings and the grid as I move, for example, towards electrification, and how I optimize across systems of systems to enable the best efficient operation of those 3 systems. So I think that's one of the areas that's got my focus in the very near term, is to bring expertise and tools and models to the community to be able to do that. Next slide just showcases, an electrification picture where I have urban and of course highlighted in the center urban area. But this is all about geographic areas and different scales. So the top right is really about a suburban area and electrification and opportunities from vehicles, buildings, and grid. Then I've got an agriculture area in the bottom right. Everything from rail and school buses and hospitals and renewable power and microgrids out in the agricultural area. Industrial areas as well, and sensitivity and resilience that they need to grid with vehicles. And then, of course, the power generation itself is incorporate more. So the systems of systems is really what's drawn my attention now. And I think we'll be pivoting towards this type of research on a broader scale. So I'm going to end there. Recognize I went over just a little bit, but look forward to any questions that you might have.
Thank you so much, Anne. I do commend you. These are really big, hard-hitting topics that you cover within our time frame. And thank you again for being with us and such a nice topic. We do have some questions on the chat. Professor Oyang is asking why sharing increases PMT, low sharing. And Professor Oyang, I encourage you to come on the conversation if you'd like to.
Okay, actually, first of all, I would like to thank Dr. Schlenker for the very nice presentation. I enjoyed it thoroughly. Just a quick question about the earlier one of the earlier slides where you mentioned about the autonomy and the sharing, sort of low sharing, high sharing. I think I probably missed some points. I was just curious why there was an earlier slide you talk about high sharing on the left and low sharing on the right, where you have low sharing, actually PMT actually increased a few percent, but then with a high sharing, the PMT remained the same. Just trying to understand the rationale behind that a little bit, if you don't mind.
Yeah, so I might put you in touch with a couple of the researchers, but again, in low sharing, high automation, it's within a single household, right? So your passengers have traveled, as I explained in a later slide, we think you have a bigger reach of the area that you'll do your activities within. And so, that might not necessarily be on my way home from work because it was close. And instead, I might divert and add an extra 4 or 5 miles different to it, right? So that's why the VMT and PMT increase in that case.
I see. Thank you. I definitely would love to hear more about it. And also, it's interesting, very interesting finding. Thank you. Yeah.
You bet.
Professor Maidani has his hand raised. Go ahead, Professor.
Yeah, thank you very much, Dr. Schlenker. This was fascinating to me to hear about the work that is done at Argonne with Polaris and this, very complicated computational models. My question is on the issue of uncertainty. So a lot of times we want to kind of inform decisions and offer these kind of results, numerical results, and computational the outcomes of these computational models to decision makers. And there could be different sources of uncertainty, like in terms of the traveler behavior or the modeling assumptions that you have. What has been your experience when you want to offer, these, let's say predicted impacts of certain decisions that they would like to make? Are they, what's the perception of on their end in terms of the uncertainty? One particular case could be this tail event. Like COVID is really a tail event if you're thinking about long-term planning, for example. So tail events like COVID could really change everything. So I just wanted to see if you can comment on how decision makers look at this concept and how they ask questions related to that.
Yeah, thanks for the question. I absolutely agree with you. Because none of us have a crystal ball, I don't believe, and can predict the future in a finite way. And so instead, our goal was to develop a framework whereby it was computationally efficient to run a multitude of scenarios, right, to address that uncertainty. You could assign certain likelihood, but to be able to cover that design space. And so even though we run 100% of our agents and 10 million agents, for example, in the Chicago region, and 3 million population plus, we can still do that in 3 or 4 hours. And so it does lend itself to lots and lots of scenarios that are run. And I guess one of the things that I insist upon with my team is the upfront engagement with the likely consumer of the information and the scenarios and the data so that it's actionable to them. And I use the CTA example, but they were the ones that lockstep with us. Here are the scenarios that I want you to do. No, not low risk perception. I want you to do a medium, right? And we also have uncertainty bounds actually on some of the analysis that we do, and that's shown to the customers of the research as well. Yeah, not predicting the future, scenario frameworks, run it iteratively such that you could narrow in and cover the design space and ensure that you have the customer, right at the hip with you all the way through.
Thank you so much.
Mm-hmm.
We have another question from CG Wang. He mentions, thank you for the nice presentation. His question is, what is your input regarding BIM applications in transportation infrastructures, especially maintenance and rehabilitation stages? How would the connected infrastructures play the role in this?
Sorry, it was breaking up just a little bit about connected infrastructure and maintenance.
CG, would you like to come in and ask your question, just so I do it justice?
Yes. First, thank you for your presentation. My question is, just to simplify this, it's like I would like to hear your comment or input regarding the BIM applications and the connected infrastructures. What's the role of these two technologies in infrastructure maintenance and rehabilitation in the future?
Not 100% positive I understand all of the question, but I would say that the connectivity and the connected infrastructure, mm-hmm. in my opinion, is one of the largest places to play for savings, and also for equity and policy determination. Right, there are, as people talk, car-free zones, curbside management, parking. Who should we bias the landscape towards for the curb? All of that plays into ITS, I think, for the system and connectivity. and the real-time information that you receive as well. But it's more important in my mind, others will disagree with me, but in my mind, it's every bit or more is important than automation. Connectivity, communication, whether it be to the cloud, whether it be vehicle to infrastructure, affords so many choices. And I would encourage you, I mean, just stop and think about your smartphone, right? With all this data flowing to you, you make decisions all the time about, you know, where I'm going to eat, where I'm going to go, you know, what location I'm going to frequent. You pick whatever you want. And so I think the same thing is true in the transportation space, that connectivity is more near term. Could very well be a lower investment threshold, and has great benefits, I think.
Well, thank you for your input.
And one last question, if I may, with respect to the system of systems and, you know, these new technologies that are being integrated in a flexible manner, what is your input with respect to energy harvesting or smart pavements, and, you know, their corresponding communication, how that may play a role into the system of systems framework that you've mentioned?
Energy harvesting from roads or from back to buildings? But
pavement's point of view, given I'm a pavement engineer.
I'm sorry, I'm breaking up again.
From roads point of view.
Yeah. So we've done pilots before in energy harvesting from roads, and whether we saw that as a viable alternative to help supplement. You know, it won't be a popular maybe, but I'll say I'm lukewarm on it. For a real viable technology that's widespread. But I do think, you know, the systems of systems look is an all hands, you know, approach, and deserves consideration. You know, the traditional things over, well, here's how you plug your electric vehicle into your charger. Well, interesting. But, you know, that's out on a land use that's in front of a building, and that building has to heat and cool and have lights for a certain number of occupants. You know, if I know state of charge of the battery and where that car needs to go afterward, you know, what's my opportunity for energy storage or resiliency if the power grid goes down, or a bus that's got a bigger size battery, and how I help on a megawatt charger for large transit or school buses or metro buses, and how I might capitalize on that depot charging for buildings or for other services that I might even be able to sell. So this total energy look and efficiency and coupling of systems needs to be a wide open lens, in my opinion, so you don't leave things on the table.
Yes, I completely agree. Thank you so much. And Professor Akai, did you have additional notes before we end this?
Yeah, that was amazing presentation. And Anne, thank you so much. And we look forward to working with you. That was very enlightening for our students. And this will be also on a YouTube for the people who could not make it because of classes. So thank you so much. We really appreciate you being with us today.
Oh, thank you. And what I will do is send over a link to the Capstone Reports and the Smart Mobility, and also to the 7 PowerPoints that were done. And they'll go into far more detail for each of the slides that I showed to give you background on that research. But thanks for the opportunity today.
Absolutely. And for the people who did not hear also, and as part of the podcast, that ICT, please check that. That was an amazing podcast too, again, Anne, and she was a visitor with us. So maybe Noel can include that with the YouTube when she sent it. So again, thank you so much, Anne.
Okay, you bet. Thank you. Everyone have a great day. Bye now.
Bye-bye.